Today we're going to talk a little bit about how we at Twitter reliably process our own Twitter Firehose. Specifically, we're going to talk about how we use Kafka to reliably process that message stream in regards to three core concepts: back pressure, bulkheading, and what I call architectural diversity. So who am I? I'm Ryan Tanner. I'm a software engineer with Twitter's data products division up in beautiful Boulder, Colorado. We're marketed under the Gnip brand, so if you've ever bought tweets, that's who you've bought it from. And we offer paid enterprise access to Twitter data in three ways: real-time streaming products, what we call insights, aggregate data answering questions like what do people who tweet about craft beer watch on TV? And our third pillar, which is what we're focusing on today, is our historical products, offering search and MapReduce-like access to the full archive of all tweets back to 2006. And that's what I work on. Now, as part of the underlying infrastructure that powers those historical products, of course, we need a read-intensive archive to run all of that. And how do we build that? We consume the Firehose. Now, just consuming the Firehose isn't that difficult. Any off-the-shelf SSD can already handle orders of magnitude more volume than ever gets pushed down our Firehose. The hard part is doing it reliably, making sure that no tweet ever gets lost, even during severe operational emergencies. Our business is such that if we lose even one tweet, our customers notice and they get upset. That's important to them, so it's important to us. Those are the business requirements we operate under. What we're going to talk about today are some of the design considerations that go into building such a system that will always eventually succeed even in the face of operational instability or unpredictable volume increases. And we're going to talk about how Kafka plays into those considerations and how we use Kafka to ensure reliable message processing. So I hope that by the end of this, you've taken away some ideas on how to handle similar situations of your own. So as I said, there are three core concepts that I want to focus on today: back pressure, bulkheading, and redundancy or redundant architecture, and how Kafka fits into each one. One of the overarching design considerations that drives our organization is keeping applications simple, our business level applications very simple, and pushing all the complexity of reliably processing messages off to Kafka and the libraries that we've internally built around it. So as we discuss these concepts, we'll be paying keen attention to how Kafka helps us deliver on them, and we're going to go into some specific examples of how we've implemented those within our Firehose processing pipeline. So if you're very familiar with Kafka, if it's old hat to you, now's a good time to check your email. I'm going to give a quick introduction to Kafka for those who might not be familiar with it. So at a high level, it's a distributed messaging system. It's designed to reliably handle large volumes of messages. Some basic concepts: we call a category of messages a topic, so you might have a topic of tweets. Producers publish messages to topics, and every topic is partitioned, and that's one of the key features of Kafka. Every topic of messages is divided into those smaller chunks called partitions, and each partition is ordered and it's immutable. Every message in a partition has a sequential ID, so we can identify a message's position within a partition, and partitions are distributed across the hosts in a Kafka cluster. We call those hosts brokers. Each partition is also replicated so that its data exists on more than one broker. Every partition has a leader and a configurable number of replicas, we call those followers, replicating data onto multiple hosts. And Kafka takes care of distributing and replicating those partitions, so should a partition leader fail, Kafka will promote a follower to take its place. It's a lot more complicated than that, but that's a nutshell. So all of this is a means to an end: reliably consuming messages in partition order, not total order, with at least once delivery. So the diagram you see right now is a crude sketch of what I've just described. So if we say we have a Kafka cluster of 3 hosts, 3 brokers, and for the moment we'll assume just one topic, we've defined that topic as having a partition factor of 3. So the topic is divided into 3 partitions, 1, 2, 3. And we've said that the topic has a replication factor of 2. So every partition is replicated onto 2 brokers. So partition 1 is on brokers A and B, partition 2 is on A and C, and partition 3 is on B and C. If broker A goes down, if it crashes, partitions 1 and 2 still have what we call in-sync replicas on brokers B and C, respectively, so we can stay in business, we can keep processing without losing any data. There are a few things to note about this design, the key takeaways. The first is that because partitions are ordered, messages will be consumed in order for a given partition. And why is this important? Since messages are consumed in order per partition, and because we can uniquely identify the position of every message within a partition, consumers always know exactly where they are in a partition. If a consumer has just processed message number 10, the consumer knows it's already consumed messages 0 through 9, but not number 11. This gives consumers total control over what they consume. Since data isn't pushed to consumers, consumers fetch data from Kafka. Later on, I'll go into how we take advantage of that. For now, it's just important to remember the key takeaway is that a pull-based system like this puts control in the hands of the consumer. So the first theme that we're going to discuss in terms of reliably processing messages today is back pressure. What is back pressure? So we think of this as the ability to bend a system without breaking the system. The nature of Twitter requires that we be able to handle immense and sometimes unplanned spikes in activity. During the Oscars, during the Super Bowl, during the World Cup. We can suddenly find ourselves consuming an order of magnitude more data than our baseline average, what we see at any given minute. Kafka serves as our shock absorber. So long as Kafka can handle whatever volume upstream services or Firehose throws at it, the downstream services, our business level applications, can consume at their own pace. So if we take this pretty little cloud to be the Twitter Firehose, as long as whatever volume it produces can be safely consumed and reliably consumed and persisted by Kafka, we're fine. Our downstream applications will consume at their own pace. They'll keep up eventually. So remember that the Kafka consumers control when and how much data they consume. They pull data from Kafka. When they're ready to process more data, the consumer will just pull it from Kafka. The consumer always stays in charge of flow control, and it can self-regulate the throughput it's able to handle. So Kafka lets consumers work at their own pace. And this gets back to something I mentioned earlier. One of our guiding design principles is keeping our applications simple and pushing the complexity and scaling concerns off to Kafka. By using Kafka as a shock absorber to moderate those spikes in volume, we free our downstream business applications from needing to handle those large spikes. So as I said, we think of this as bend, don't break. It's okay if that unexpected flood of data causes our average latency to spike, so long as we eventually succeed, so long as we eventually deliver those tweets to our customers. We rely on Kafka to help us keep that guarantee. That's our SLA. Why is that important? Well, like I just said, because our customers say so. And this is where you have to talk to your product managers to figure out what your SLA is. What's your acceptable behavior during abnormal operating conditions? Our business is such that if we lose a tweet, if we break the system, our customers get upset. But if we only have a delay, if we bend the system, we can tolerate that. It all comes down to your business requirements. So, we're going to move on to the second concept, and of course we heard all about this earlier this morning during Jonas's presentation. Bulkheading is a fancy name for failure isolation, ensuring that the failure of any one component, or even multiple components, doesn't take down the entire system. And bulkheading most typically takes the form of redundancy in a system like this. And redundancy in a stream processing system means replication. And in Kafka, the unit of replication is the partition. That's really core to Kafka. Every topic is partitioned and replicated across the cluster. And like I've said a couple of times now, we try very hard to keep that kind of complexity contained within Kafka. The value of Kafka is not just that it handles this kind of complexity, it's that we can use it to solely handle this kind of complexity. Our application code just becomes that much simpler, and we can develop those applications where we actually deliver business value much more rapidly. So Kafka bulkheads against the failure of any given host through replication, but what's also key about Kafka is we can use it to build bulkheads around our applications. So to give a concrete example, which is what you see on the slide right now, we have a stage in our Firehose processing architecture that consumes Firehose messages from two independent Kafka clusters, merges them, dedupes within a given window, and publishes them onto another cluster. So if you take the left-hand side of the slide, that's the Kafka logo for those not familiar with it. So if you take those two independent Kafka clusters, and then in the middle we have our deduping applications, we have that application cluster. They're going to pull some set number of messages from both independent clusters representing the Firehose. They're going to dedupe within that window and publish it off to the next cluster. Now, should any one of these application instances fail, all of its in-flight messages are safely on the original Kafka cluster. We don't actually act them until they're successfully handed off to the next stage, the next Kafka cluster. So we've built this bulkhead around our application, which means that the application is freed from having to worry about a lot of different kind of failure scenarios. If one of them goes down, we know that we'll just reprocess later on, that's fine. So should any one of these application instances fail, all its in-flight messages are still on the original cluster. Back in the early Kafka days, and I think GNIP started using Kafka back around 0.7, GNIP wrote its own consumer to handle all of this, because at the time, the standard high-level consumer would commit its offset as soon as messages were taken off the prefetch queue. We wrote a custom consumer that allows us to commit our offset based on business logic instead. So our Kafka consumers only commit their offset after successfully handing that batch of messages off to the next stage. And since we require all in-sync replicas to successfully receive a message before acting back to the publisher, which would be the application instances, we know that until a message has been received by all the downstream Kafka brokers, it's still safely on the upstream brokers and will just be reprocessed if there's any kind of hiccup in the middle of that pipeline. And this takes us back to our overarching theme of simple applications and a complex messaging system. We don't need robust failure handling or dynamic partitioning in our applications. We can just let them fail, knowing that any in-flight messages will just be reprocessed later on once the system has recovered. If any of these deduping machines crashes or it finds itself unable to reach its downstream Kafka broker, if there's a network partition, it'll get reprocessed later on. It's fine. So this is a good example of how we've used Kafka to build bulkheads around our applications, allowing for the failure of any single application instance without risking any data loss. So that's an example of redundancy and bulkheading at the host level, but of course you can also run your entire cluster independently. And so in our Firehose processing system, we're redundant at two levels. Kafka is replicating its partitions within the cluster, but we're also running parallel independent chains. So what you just saw was how we merge those pipelines back together. But the entire pipeline up until that is run entirely in parallel. It's completely redundant. And we think of this as brute force bulkheading. It's exceedingly rare, but we could lose an entire ingest pipeline and the other would keep us in business. So we could lose not just hosts in those pipelines, but again, the entire pipeline or the Firehose connection. We could find that one of our Amazon availability zones loses network ingest. These are failure scenarios that happen in the real world. And there are other advantages to building redundancy at the pipeline level like this. You can simplify much of your failure handling within each pipeline. Since every host has an identical twin in the other pipeline, we're less concerned about individual failures of any given host. This is also great from an operational perspective as the on-call engineer. If a host fails at 3 a.m., but it's not seeing any customer impact, there's no reason for PagerDuty to wake you up. You can just kick that can down the road till business hours, fix it later on. So this is the most ambiguous theme in the presentation, and it's the one that has nothing to do with Kafka, and I'll explain exactly what that means. So I've spoken at length about the need for redundancy and replication, but that only guards against certain kinds of failure. If it turns out you have a bug or a design flaw, all the redundancy in the world has gotten you is just redundant bugs. You've replicated your flaw across multiple hosts. So diversity within your architecture can help you avoid that scenario. If we were to inadvertently push a bug in our Kafka consumer or in one of our application instances that caused data loss and somehow not notice until it hit production, all the redundancy in the world isn't going to save us in that scenario. Now, this is hypothetical. This hasn't actually happened, but it's important to plan for it. A heterogeneous system reduces the chance that a single bug or a single flaw will ripple across your system and cause problems down the pipeline. So while we rely heavily on Kafka, and that's very rarely caused us any problems, we have backups. We have alternate ingest pipelines that don't rely on Kafka. And so again, let's go back to a concrete example. We rely on Kafka, we trust it, but just in case we found ourselves in a scenario where Kafka lost data somehow, we have a backup plan. We have a set of hosts constantly consuming the Firehose and flushing it to Amazon S3 in batches. If we ever have an operational issue with our Kafka clusters, if we lost all the in-sync replicas on a given partition, we can replay chunks of the Firehose off of S3, re-ingesting them at the top of the pipeline. So this is what I'm talking about by diversity. We aren't assuming that Kafka will never fail. It rarely does, enough that this backup system is almost never invoked. I can't remember the last time we had to use it. But building this backup means we haven't put all of our eggs in one basket. So when I talk about a heterogeneous system, I'm talking about not relying on a single piece of software to always perform perfectly, or not relying on your whole architecture to always perform perfectly. It may be nearly so, and that's our experience with Kafka, definitely, but sometimes your use case requires you to be very paranoid in ensuring against data loss. So how do we tie it all together? The pitch for this presentation, of course, was how we get a tweet from Firehose to archive. So let's talk about how that actually happens. So you're going to see here some of the pieces I've just shown you tie it all together. So if we take the left-hand side, our two independent Firehose connections, and I'm sure some of you are saying, well, you're Twitter, why are you consuming your own Firehose? As I said, this is GNIP. It was an acquisition 2.5, 3 years ago. So most of this infrastructure still exists off in GNIP's own Amazon VPCs. It's not part of mainline Twitter infrastructure. So we're consuming the Twitter Firehose dually, redundantly, and we're consuming it as fast as we can and pumping it into Kafka. So at that point, in that third column, we have two independent Kafka clusters, and they each hold duplicate Firehoses. We merge them, so this is where you saw when I was talking about building bulkheads around applications. This is where you see that in the third through fifth column. We merge those two independent Firehoses and publish them down to a third Firehose. That Firehose now is what we call clean, and it consists of a single deduped Firehose, the result of two independent consumption pipelines, and now it's available for applications. So isn't that a lot of complexity just to consume tweets, keeping in mind that the diagram I just showed you is quite a simplification. All told, it's about 40 machines just in production. So like I said at the start, consuming the Firehose is easy because any off-the-shelf SSD has more than enough write capacity to handle it without breaking a sweat. But consuming it reliably and guarding against operational failure is a much more difficult problem. Every stage has to have back pressure, it has to have redundancy. It requires fault tolerance as a first-class citizen. And I know it's a slogan that gets bandied about a lot, but you really do have to be ready for the failure of any given host or any given component in your architecture or a whole side of your architecture. It also requires robust validation and quality assurance, and I want to talk briefly about some of the strategies we employ there. So all the redundancy and back pressure is great, but how do you make sure you actually got it right? We have a truly phenomenal QE team up in Boulder. It's actually about 10% of the total engineering force in our department is just QE, and they work very hard to keep us honest. So for example, every 2 weeks, we actually generate a mock Firehose that is triple the highest volume Twitter has ever seen. And we push it through this entire system. Triple the highest volume we've ever seen. We push it through the entire system, and we make sure that not just our consumption pipeline can reliably handle that level of volume, but that every downstream application can reliably handle that volume without falling over. I mentioned briefly earlier on that we don't really alert on the failure of a single host, and that's important because no single host matters all that much to us, because it's redundant and duplicated and there's another twin somewhere else. Our monitoring strategy is far, far simpler. We don't care about the failure of a single host. If it fails at 3 o'clock in the morning, we'll worry about it the next day. So that really, as the on-call engineer, makes life a lot better. So to recap, when you're designing a large-scale message processing pipeline, you need to think about back pressure to withstand increased volume and operational failures, bulkheading to isolate those failures, and redundancy and diversity to prevent those failures from rippling across your entire system. So it's a pretty compressed presentation. I don't have a full 50 minutes of content. I'm going to give you some of your time back today. But I will allow time for questions. And I'm also going to make the obligatory recruiting pitch. If you'd like to join us up in Boulder, please come talk to me afterwards. I'd love to discuss the opportunities we've got up there. And we've also got a beautiful new office, and that's not far off from the view from our patio. So thanks for coming today. Questions?
Yeah, so you said you have these DDuped jobs that are...
I'm sorry, can you speak up a bit?
So the DDuped jobs, if they fail in between publishing to Kafka and committing, does that mean you've got dupes in the clean stream?
If they so that's we accept that. It's the downstream one is, we call it deduped, but it's really mostly deduped, and downstream applications have to handle some dupes. We just don't want complete dupes. We don't want every message to be duplicated. And so, for instance, in previous iterations, this not only powered our historical products, it powered all of our streaming products. And so that eventually was published out to our customers. And our expectation with them is just that they need to be able to handle some minor level of dupes. It's very difficult to dedupe perfectly in this kind of system, especially because it's not unheard of within the Twitter Firehose to find one of our ingest pipelines massively out of phase and very, very delayed. It's also not unheard of for us to suddenly get a tweet that may have been created 5, 10, 30 minutes ago come through our pipeline. And so at some level, a dupe just has to be expected down the pipeline. We just don't want every message to be duplicated. Yes?
How much history do you keep on your Kafka?
Those intermediate topics, it works out to about 8 hours. It's not time-based, it's number of messages, but that's on average. The downstream one at the end of that pipeline, I don't remember what it's set to now, but I think it's about 18 hours. Again, it's based on a number of messages, not a time window, but that's roughly what it comes to. Yes? So every one of the Twitter has what we call snowflake IDs, and one of the unique properties of snowflake ID, it's how we uniquely identify messages. It's how we generate the message IDs. One of the unique properties of snowflakes is that though they are not sequential integers, they are guaranteed to be in order. So we can always determine the order of tweets based on their ID, even though they're not just a sequential ID. So that's how we determine it. Yes?
So beyond the 8 hours, do you like archive in HDFS?
So if we were to fall out of that 8-hour window, that's where that, when I mentioned that we have those set of machines slurping the Firehose up to S3, that's where that comes in, because that bucket we can retain for, it's set to 30 or 90 days, I don't remember right now, but a very long period of time. So that's our true backup if we actually needed to completely re-ingest some period of time.
You're saying no HDFS?
No, we don't have HDFS. Actually, the archive of tweets that powers our historical products is literally JSON files on an S3 bucket. That's it. It's the most basic, unfancy system anyone's ever come up with. There's extremely little that is fancy or sexy or even new in this system. One thing that's important to remember about this architecture is it's now pushing 7 years old. Kafka was introduced to it about 4 years ago, and I don't know if Jamie Greer is in the audience, but he had a talk on Flink earlier today. He's ex-GNIP, and he was actually one of the people who put Kafka into the system 4 or so years ago. So the system's been around for a very long time. I don't know when we last did feature work on it. It has one job only, and it does it fine. It's rock solid. We don't put those intermediate applications, the ones that consume the Firehose and dedupe, and there are some others that I left out of the diagram. They are literally just a jar file sitting on an EC2 instance. There's nothing fancy about it. Sure.
Instead of writing from source Kafka topics to new Kafka topics, you're choosing to write from source
source Kafka clusters to new clusters. What drove that decision?
I think that just comes back to the paranoia aspect. We could just loop it back onto the same clusters, but we want them to truly be independent so that if there is any kind of failure in one of those pipelines, it doesn't cascade down, down to the downstream applications. We want them to be completely isolated. Yes? So this is where our QE team comes into play. They're constantly validating the final archive. Well, there's a few ways. One is they're consuming off that final Kafka cluster, and then actually checking it back against our source of truth, which is off in Twitter. They're also scrubbing our archive on a continual basis and doing the same, checking that against the source of truth to make sure that every tweet actually has gotten there eventually. So if we lose a tweet, we'll get paged about it. We'll get notified. Any other questions? Yes?
You may have mentioned it, but how do the downstream applications consume the stream of tweets? Are they all connected to that final Kafka cluster, and you just have lots of connections to it, lots of consumers, or how do you do that?
Lots of consumers. They all consume off that one final cluster. And again, this is one of the properties of Kafka. You can have many consumers. Each one has its own partition offset, so they can all consume at their own pace. Yes?
How do you guys manage your topic partitions, like the keys? How do you choose the keys you're going to use?
The key is just the tweet ID, and all of our topics are statically partitioned. There's nothing dynamic about any of it. We don't have any elasticity in this particular system. It's just massively over-provisioned. We barely spike any of the metrics, network I/O, disk I/O. We barely use any of it on an average day. And then if we see a spike, we'll maybe hit 20, 30% network I/O utilization. It's just massively over-provisioned, so we don't need a lot of elasticity or the ability to dynamically scale up those clusters. Yes?
I understand that tweets are fairly small, but do you have any use cases or systems where you run into the size limitations of the Kafka message?
So one thing to note is that our tweet payload is actually quite large. It's not just the 140 characters. It's a lot of denormalized data, so we're including things like clout data about the user that actually generated that tweet. We're including their full profile. We're including if there's a URL, we actually unwind it out a certain number of levels beyond just the Twitter link shortener, the TICO. So we unwind that, including the HTML title and HTML description. But beyond that, we've never run into the size limitation. That's a good question, though. I don't have a good answer for you on that. Yes?
You mentioned the mock Firehose.
Mm-hmm.
I'm curious of a high level what that looks like to generate that much data.
Good question. So we call it the mockerator, and all of our applications actually end in ator. I don't know why. And so it's based on real tweets, so it downloads real tweets from our archive. It just generates new IDs for them, fake IDs. And we publish it through our staging pipeline. And our staging pipeline is identical to our production pipeline. And so as long as those IDs are different, nothing else in the system until it gets down to very downstream applications that are doing analysis on it, nothing else in the system is actually looking into the payload. It just looks at the ID. Yes?
What is your monitoring solution for these Kafka clusters? How do you keep track of under-replicated partitions, offline partitions?
Those are all published into Nagios. I don't actually know exactly how that works, but we have some kind of shim that's publishing that into Nagios, and then that in turn goes off to PagerDuty if it needs to. Yes?
You mentioned that you run a static number of partitions. Can you be more specific about how many partitions you use?
Sure. So I believe we partitioned the Firehose into 32 partitions, and each partition is replicated onto 3 hosts. Another thing to note is that in our configuration, we require when we produce a message into Kafka, we require every in-sync replica, each of those 3 replicas, to act the new message before it's actually act all the way off to the producer, so that when a producer publishes a message, it's persisted onto 3 brokers. In fact, by the time a message flows through that entire system, every tweet has been persisted, I want to say 7 times to disk before it's even made available to a downstream consuming application. Yes?
When you're doing your Firehose for validation in QE, are you literally just testing to see if it will break, or are you doing kind of like value-based engineering where you're seeing what parts are stressed and if you're meeting key performance parameters to guide your forward motion?
Yeah, so we monitor at a lot of different points to see what we mostly look for is lag. So we're looking for where in these different, at the different points in the application, are we lagging outside of some expected threshold. So every application, both within this architecture and the downstream applications, publishes to Nagios the current average time over the last 15 seconds or so, I believe. I don't remember exactly what it's configured to. Over some recent time window, the average creation time of the tweets it's seeing, that gets published to Nagios. And if that falls behind current clock time by more than some given threshold, we'll alert on it. And we have that at not just the final stage, but at every single application the tweet passes through on its way. So we can see where exactly there's any lag cropping up in the system.
Can you model that change between your normal operations and when you're operating at your hypothetical like apocalypse day scenario?
What do you mean by that?
Like, does it change significantly when you do the Firehose like at 3x or?
Generally not, and that's mostly a factor of how over-provisioned the system actually is. So to get from Firehose on this slide, there we go. So to get from Firehose to that final cluster, our SLA is 2 seconds, and I think we normally see about 0.2 seconds total time. So that gives us a lot of headroom in terms of our business requirements. And if we get anywhere near that during our QE phases every 2 weeks, then we'll know well ahead of time before this would actually impact our business. I don't think we've seen any major problems with that lately, partly because the system is again, just so massively over-provisioned. We could run it on probably half or a quarter the number of boxes we do. We're just very paranoid, and ultimately, 40 EC2 instances compared to what it's powering is a drop in the bucket. It's worth it for the peace of mind. Yes?
Can you share a little bit about the spec of the broker, like in terms of CPU and RAM?
I'm sorry, I couldn't quite hear you.
The broker on the Kafka cluster, can you share a little bit about how big they are in terms of how many CPU and the RAM?
Sure, they're EC2 M4X large instances, and I don't remember off the top of my head exactly how those are configured. I want to say 16 gigs of RAM and 8 virtual CPUs, but don't quote me on that.
But it's not a large machine, it's a usual medium size.
Yeah, it's a good-sized machine, but it's not gargantuan. All right, well, I guess unless I don't see a hand up, thanks for your questions, and I'll be around. Feel free to come talk to me. And like I said, if you'd like to come to beautiful Colorado and join us working on this, please come talk to me. Thanks.